Hello, hello. Welcome back to another seminar for Physics 3-4 at the VCE Summer School 2023. It's me again, Sai Pamaraju. Um, and in the last seminar, if you've watched it already, we covered a fundamental concept that was relatively newfound in physics, and that was special relativity. By new, I mean in the 1900s, which in a physics context is quite new. Today, in this seminar, we're going to continue a similar trend and look at another more recent field of physics known as quantum physics. I use that word quantum quite loosely here. There's obviously a lot more involved in quantum physics than what I have shown in this lesson. We will only scratch the surface in this seminar, so it's important to note that there's plenty more. There's so much more that that quantum physics encapsulates. So our focus is predominantly on the nature of light and how two contradictory models that describe the nature of light can both be used to explain the stuff that we see around us. So, and all of this goes back to quantum mechanics. I will quantum physics rather. I will describe exactly what that means in a second. So, what the agenda is for today is that there'll be a brief introduction, which is related to the quantum nature of light and matter. Secondly, I will discuss the second and third things I wanted to discuss here were relating to pieces of evidence that describe that support each of the models of each of the two models of light that we see. So one is the photoelectric effect, which describes the particle, which is supported by the particle nature of light, and the other one is Young's double slit experiment, which is supported by the wave model of light. We'll see what all these terms mean in a second. So let's get straight into it. So the motivation behind this is that in the 20th century, before the 20th century, light was thought to have been described by what are called Maxwell's equations. So Maxwell's equations are the ones that describe how electric and magnetic fields propagate throughout our vacuum, throughout a vacuum or through some medium. You may not have seen Maxwell's equations. They look quite nasty, and we certainly don't cover them in 3-4 physics, but it's important to know of them in a qualitative way. So far, until that point, light was thought to have been described by Maxwell's equations. In the 20th century, however, some very clever physicists decided to challenge this model, and because they observed phenomena that could not be described by these equations. In comes a German gentleman called Max Planck, and he theorizes that these phenomena are best described if light is sort of emitted in discrete packets. If light is sort of distributed in discrete packets, these are what are called quanta. So maybe you can see where quantum physics comes from. The energy of each of that quantum of light, each discrete packet of light, E, denoted capital E, he said was given by this equation. So E equals H times F. Okay, so what is H? H is a constant, much like Newton's gravitational constant, if you've dealt with gravitation in the past. But H is what's called Planck's constant. It has units of joule seconds, and it has a value of 6.63 by 10 to the minus 34. So it's a very small number. In joule seconds, it has a value of 6.63 by 10 to the minus 34. Generally, in VCAR exams, this will probably be the smallest number you will see. So that's another way of checking your answers in exams. If you get an answer that's smaller than 6.63 by 10 to the minus 34, most of the time you will need to go back and check that you haven't done anything wrong. Anyway, H is Planck's constant, named after Planck, obviously. And F is the frequency of light measured in hertz. So here we're assuming that light has a frequency, which means that we are assuming that this is a wave already. So wave model, because only things that are waves have an associated frequency. So, as I mentioned before, there exist two contradictory models for the nature of light. Here we've assumed the wave one, just for the purpose of this equation, but there are two contradictory models. There's the wave model, which I've just described, and there's also the particle model. In some situations, light appears to behave like a wave, and in some others, it behaves like a particle. We will see examples of those two just in a second. So it's basically, the problem is that light is going through multiple personality disorder. So it is going through, sometimes it behaves like a wave, sometimes it behaves like a particle. When does it do what? And that's, when does it do what? Well, we don't really know. It sometimes it behaves however it feels like when it feels it. Anyway, so another thing, so what we can do is, since we've assumed a wave model here, when we've written this equation E equals HF, these discrete packets are thought as being propagating as waves. So you can think of these to be sort of packets of waves that kind of look like this. It's a very poor illustration, but I'm sorry. So we have a discrete set of particles that together overall propagate as a wave. You can think of it as like that. Anyway, since we're assuming that we're dealing with waves here, we can employ the wave equation, and we can see that the speed of light, c, is equal to the frequency of the emitted light. When I say light, it's interchangeable with electromagnetic radiation. So it includes all the forms of radiation. So X-rays, gamma rays, anything in the electromagnetic spectrum can be described by this equation. So C equals F times lambda. Lambda here is the wavelength of the light. So it has a frequency and a wavelength, therefore we know that it's a wave straight away. So this is a frequency, and C is equal to the speed of light. Which we know. No worries. Okay, so that's so E equals HF. But C equals F lambda. So if we rearrange this equation, the wave equation, if we know that C is equal to F lambda, and we know that E equals HF. So let's just divide both sides of the left equation by lambda, and we'll see that F is C, pun not intended. F equals C over lambda, and we'll also see that E is equal to HF. So now what we can do is we can plug in the definition of F, we can plug in what F is equal to into this equation here. So let's do that. So then we can write E equals HC on lambda. This is another equivalent expression which for the energy of each quantum, energy of each discrete packet of light. It's just written in terms of in terms of the speed of light and its wavelength. So those two expressions that are in the red box, they are equivalent. They're just written differently. Okay, so that's the basic sort of motivation behind why we think of light as existing in two different models, the wave and the particle model. Now let's look at pieces of evidence that support this, that support each type of model. Starting from what's called the photoelectric effect. The photoelectric effect is something that Einstein came up with in the I'm not exactly sure when. I think it was in the early 1900s, but um, and it's a common myth that he won the Nobel Prize for special relativity, but that's wrong. He actually won it for this photoelectric effect because it really revolutionized the way physicists at the time viewed quantum mechanics, quantum physics. So the photoelectric effect is an example of a phenomenon that cannot be explained by the wave model. Um, okay, so what does that mean? Um, so this is what the photoelectric effect basically entails. So we have a piece of metal on the right here. I've drawn it here. This is a piece of metal. It can be whatever you want it to be, as long as it's a metal. And you have a source of light here on the left. That's my drawing of a torch light, by the way. It's poor. So the idea is we switch on the light and we let it shine on this metal. And if we were to measure, if we were to measure the amount of current or connect it up to a circuit, what we'll see is the that the surface of the metal has a lot of electrons on it, as it should, right? Well, it's a material, so it does have protons, neutrons, and electrons. So the surface atoms would have electrons. The moment we shine some light on this, what we notice is that electrons get liberated off the off the off the surface of the metal. So we kind of, electrons kind of jump off the surface of the metal. If the if the frequency of the light is high enough, so if the frequency of the sorry, no, if the intensity of the light is high enough, then you see that more electrons are liberated. Think of that in terms of particles. Let's say we had a so-called particle of light, which is, typically the photon, which is given the symbol gamma. So if this photon hits the surface of the metal, it has sufficient energy. So let's say energy of the light, rather energy of the light, energy of light high enough means that more electrons are liberated from the surface of the metal. So the stronger the photon is, the stronger the energy of the higher the energy of the emitted electron is. So the more photons you have, the more electrons you're going to liberate. The more electrons, so the more photons you have with sufficient energy, the more electrons you're going to emit, that you're going to liberate from the surface of that metal. So that's what the photoelectric effect is. There are some terms here which we need to be familiar with. So an electron that is emitted from that surface of the metal as a consequence of the photon hitting the surface of the metal is what's called a photoelectron. So when the electron comes off, this is what's called a photoelectron. So photo means generally stuff to do with light. So photoelectron means electron that has left the surface of a metal as a result of the photon hitting it and liberating the electron. So that's what a photoelectron is. Now, if we had this set up and we sort of connected it up to a circuit, we had some wires going around and some funky setup here with the power supply. If I connected it up with a circuit, say we had something crazy like this, then what we can see is that these electrons will flow through will flow through these wires that we've set up here, right? So if we set it up in such a way that these electrons are allowed to flow through the circuit, this is what's called a photocurrent. So photocurrent is a photocurrent is the current that's induced as a result, current produced as a result of electrons being liberated from the surface of the metal. But one thing you should note is one last thing you should note is that not every photon is gonna liberate an electron, right? There's two criteria that a photon has to meet, such that there's a criteria that a photon has to meet to liberate the electron off that surface. So, and that is that the photon must have sufficient energy to liberate the electron. Okay, so what does sufficient energy mean? I've just defined it kind of vaguely. It doesn't seem to make sense, right? And the answer to that depends entirely on the metal that's being looked at. So each metal has what's called a work function. Work function. So the work function is specific to a metal. Oh, this font is looking very funny. To a metal. So it depends on the metal that we're looking at. And what it is it's the minimum amount of energy needed to liberate for those of you who aren't familiar with that term, is to free electrons from the surface of the metal. Liberate electrons from the surface of the metal. Okay, so that's that. So the work function is generally denoted by phi, the Greek letter phi. This is the Greek letter phi. And what Einstein said is that each metal has its own work function. Work function is a unit of energy, so it's either measured in joules or another unit, which is the electron volt. Okay, so that's that work function. So if the photon energy is greater than the work function, then you're going to have an photoelectron emitted. If not, then nothing happens, and we have a boring experiment. Okay, so how does this actually explain the particle model? Well, what we notice is that if we increase the intensity of the light wave, sorry, I said wave, I meant particle. If we increase the intensity of the light source, so increased intensity of the light source, so increased intensity of the light source means that more photoelectrons, I'll abbreviate to PEs, photoelectrons emitted. So the more, so the brighter we make it, the brighter we make this light, the more photons are going to hit metals, more photons will have energy to liberate electrons from the surface, and so more photoelectrons are emitted. And experimentally we can see that that there is a one-to-one correspondence between the photon that's liberated and the electron that's coming off. So all of this suggests that light behaves like a particle in this case. So this can't be explained by the wave model. It's only explainable by the particle model. You know, if you change the frequency of the light, that doesn't make a difference. It's just the intensity is what makes the difference. So if a different frequency corresponds to a different wavelength. So if you put a light of a different color here and did the same thing, that doesn't change the result. You're still gonna have the photoelectron emission being directly proportional to the intensity of your light source. So this suggests that light behaves as a particle in this case. Okay, all well and good. What's the confusion? Light does behave as a particle. Hang on a minute. There was another gentleman by the name of Thomas Young, who came up with a different experiment in a slightly different time period. And this actually supports the wave model of light. How does it do that? What's involved? Let's have a look. This diagram does look quite confusing, I know. And I've deliberately set it up so that I can sort of walk you through it as best as I can. So let's say we have a light source here on the left. I'll label it L for light, a light source. And we have a setup with, we have a barrier with two slits for the light to pass through. Okay, so that these are labeled by S1 and S2. On the other side, on the opposite side, we have in red here, that's a screen. This is what's called a screen. This is just a screen, like much like your TV screen or your projector screen, whatever. The idea is to let this light source shine. What happens then is that the light waves pass through both slits like this, and then they will both sort of combine at the screen, much like I've shown here. The purple and the green lines sort of meet at this point P. They're going to do that throughout the screen. So you might have a point here. You're going to have, because the waves spread out. These are just two waves that I've drawn, but you're going to have multiple meeting points. Now, at some points, at some points you will see waves that, so here if we assume that light comprises of waves. So before we do that, let's consider what happens if light was just a particle. If light was just a particle, it would only go through one of these slits and just sort of deposit there. But that's not what happens. Instead, what we see is something that looks like this. If we did this double slit experiment with what's called monochromatic light, monochromatic meaning just one color, monochromatic. It's important that this has to be monochromatic light because we don't want to mess up our wavelengths. Monochromatic means one color. So in the below diagram, they've used green, green light. So that because they know it's, I mean, you know the wavelength of all the colors, but of light, but the value of the wavelength is actually important, which you'll probably see in the future. But what you see here are a series of bright bands like this one, bright band, bright band, bright band. But you also have dark bands that are like this. You have the dark sort of fringes on the you have sets of alternating bright and dark fringes. Now, why does that happen? If we go back up, I said before that the light waves sort of meet, meet at different points along the screen like this, and uh, and depending on where this is, where these points are, you're gonna have the the waves, the two waves either add up, you know, so you can have both of them being in sync with each other. We call it in phase with each other. So the purple and the green sort of add together, and so the resulting amplitude is a bigger wave. If two waves of the same size stack up together, they pile up, and the amplitude of the resulting wave is bigger. You have points like that, but what you also have are points where the waves are what are called out of phase. So here in the first example, our waves are in phase. In phase means they are in sync with each other. They're not sort of offset by a certain amount. But then you'll have other points um, where the peak of one wave coincides with the trough of another wave, of the other of the wave from the other slit. So you have the peak from one wave, and you also have the trough from the other one, and they both sort of cancel each other out. So this so that's where you have a canceling out. Okay, so this is where they're out of phase. So you won't get any wave here. You're going to have a zero. You're just going to have a flat. You're not going to have any wave there because the two wave fronts cancel each other out. So out of phase. So this is what's called constructive interference, the first one. Constructive interference. Constructive is when the amplitudes of the two waves add together, and interference. And destructive interference is the other one, if you hadn't already worked that out. Destructive means they cancel each other out. So maybe if you look at the diffraction pattern now, this is what's called a diffraction pattern. Diffraction means the spreading of waves as they sort of pass through a set of slits, or some sort of hole in some in some surface. So diffraction pattern is what this is. So in the diffraction pattern, maybe you can see why we have a series of alternating bright and dark bands. So the bright bands are where constructive interference occurs. And the dark bands are where destructive interference occurs. So another quantity that's really, really important when we're working with this experiment is that of path difference. So path difference refers in a rough sense to the difference in the distance traveled by each of those two waves. So the difference in the distance between that's traveled by the purple and the green waves. So difference in distance traveled by each of the wave fronts. Okay, so that's what a path difference is. Now, path differences generally are measured relative to what's called this big bright band in the middle, which I've indicated here is what's called the central maximum. My annotations are going to get really confusing. My apologies for that. So central maximum. What we know is that the path difference is going to be an integer multiple of the wavelength when it's so the path difference is going to be an integer multiple of the wavelength wherever constructive interference happens. So whenever constructive interference happens, the path difference between between the purple and the green is going to be an integer multiple of the wavelength. So that's what n represents here. So n is an element of z. So n can be 0, 1, 2, blah, 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 so on and so forth. So z plus. Oh, z actually, it can be anything. It can because these are measured relative to the central maximum, that you can go either side of it. So you can also include negative numbers. So, you can have dot, 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 -1, 0, 1, dot, 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 so on and so forth. Integer multiples. Now, at every half a wavelength, you're going to have destructive interference. So every half of a wavelength, you're going to have the amplitudes of the two waves sort of canceling each other out, and hence you get the dark fringes. This happens at half a wavelength, at half of each wavelength. So n is still an integer, except n equals blah, 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 -1, 0, 1, blah, 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 and so on and so forth. This is where you get dark fringes. So it's important to note those two. So for every integer multiple of the wavelength, so lambda is the wavelength of the light that we are observing. This is why I said that the wavelength is actually something that's a useful quantity, which is why we have to pay attention to the color of the light that we're using. Wavelength of the light source, wavelength of light, incident light, the light that is shone onto the screen. Cool. So this is why we make it monochromatic. If we used white light, say, you're gonna have as the light sort of goes through the slits, you're gonna have it split up into its constituent colors. So you're gonna see a rainbow all the time. So a bit of any Pink Floyd fans, you'd love it, but anyone else, probably not. Probably not the effect you'd want to observe. Okay. So that's that. So this model supports the wave-like nature of light. So I know I haven't elaborated too much in too much detail about the wave-like nature of light, and that's because that's something that I can't do in the time constraints that we have. I would strongly recommend that you look through wave mechanics, or wave physics, wave optics, or whatever it's called these days. It should certainly be covered before you cover the double slit experiment in class. So that's that. So that's how Young's double slit experiment works. Now, if you ask which one is correct, I will say they're both correct in their own ways, and there's no absolute answer. Both models are supported by different sets of experiments, and there's no way we can tell whether one is right or not. So that's that. Okay, now to the supposedly fun stuff. This is a qualitative question, because generally what they do in VCAR exams is they tend to see how well you know your stuff qualitatively rather than doing calculations. Okay, so this is something that we did cover earlier today, but it's worth refreshing once again. So light can be described. So what the question asks is that it says that light can be described by a wave model and also by a particle or photon model. We discussed both of these before. The rapid emission of photoelectrons at very low light intensities supports one of these models, but not the other. Identify the model that is supported, giving a reason for your answer. So I would encourage you to pause the video, have a little think about it, and then resume when you feel ready to provide the solution. I will give you a few seconds for this. So I'm assuming you've had a go at it. So what model did people think that it supported? Well, it would be the It would be the photon model, right? The particle model. Um, why is that the case? Why is it the photon model? So the rapid emission of photoelectrons at very low light intensities. Why is it the particle model? It's because it's because sorry, my apologies. I am experiencing some difficulties here, technical difficulties. So one of the models is supported, but the other one is not. Which one is it? Is it the particle model or the wave model? Um, so the low light intensities makes me think that it is the wave model,